asymptotic result. We want to see what happens if I take and see it in a final sample simulation. We want to see the relation between that particular process and the ARIMA process. So that would be 0.4. Then we want to see what happens if I try to forecast this process using ARIMA, and then some conclusions. So let's start just talking about what we mean by long memory. And I would say that in time series literature, this started with this paper of Granger in 1966. And what he did, he took a bunch of economic series, calculating the spectrum of this, so going to the frequency domain. And he noticed that they seem to have a pole at the origin, so they seem to diverge when you go to, in the spectrum when they go to zero. So we now know this implies that it has long-lasting autocorrelation. So and I'm going to show you in a next slide what we mean by this hyperbolic decay. So they seem to fall a little slower than what standard models allow us to do. So that's, I would say that's when I started the attention schedule, when we start saying we may have to model this hyperbolic decay because of the correlation. It seems to have been detected in many time series, in economics and finance, some other disciplines, some real flows, for instance, GDP, inflation, that kind of series. And we know now that it has implications for estimation and forecasting, so we have to be actually careful what we, when we according to the long memory, we have to do probably something else. So that's how we started. And as I told you, I want to briefly what we mean by this hyperbolic decay. So first we started just kind of in this with the blue and the red line. So this is the correlation function. One way to think about this function is how many periods does it take a shock to evaporate, to dissipate in time. So before we had the standard, the AR1 process, that's the blue one. So as you can see here, and this is a persistent 0.8, it's quite persistent for I0 processes. And still after 20 lags, 20 periods, sorry, the shock can also pretty much disappear after that. Then on the other side, we have the I1 process, so the unit roots. Another kind of processes, we have many tests. We have to estimate we have this kind of process, these unit root processes, some other physical properties. So for a time, we were living in between kind of going to zero really, really fast, or never going to zero, kind of the shock never disappeared. And then when Granger did the results, say, well, we may have something kind of in the middle, and that's what the long memory models try to capture, and that's what we obtain when we start taking some fractional differences. So now what we're doing is, instead of just the pure difference, we are applying some exponent to that difference. And what we obtain with that, we can see that in the yellow and the purple lines. So we obtain something that goes to zero. It's not like the unit-rooted process, but it goes lower than what would be the case for the I0. So even after 50 periods, we are still not quite at zero. We are going there, but we are not yet there. We are going in a matter slowly. That will mean by hyperbolic decay. So that's kind of the idea. We are going to study these kind of processes that go to zero in a slowly kind of way. So that's the idea. And as I told you at the beginning, I was interested in studying these kind of processes, what this long memory was. And so the dissertation kind of contributes in three branches. So the first chapter is just studying. So we have good economic reasons, I would say, of why we have a series that is an I0 process, or why it's an I1 process. We don't have that many to say why we may have long memory. One of the most typical use, and is cross-sectional aggregation result. So what I wanted to do and what we did in the first chapter, co-authored with Niels, is studying a little more in what this aggregation result actually signifies for long memory processes. So that's the first chapter. Then for the second chapter, it's something that we kind of following from the first chapter. We must see that this aggregated process is not an ARIMA. But still, we were interested in seeing how well an ARIMA would forecast this aggregated process. So that's what I did in the second chapter. So I know it's not an ARIMA, but still, ARIMA is probably a good model to do long memory. Let's try to forecast and see how it does. So that's kind of the idea for the second chapter. And the third chapter is going back to estimation. So now in this chapter, what we have is this unbalanced regression. So we have a long memory kind of on the right side of the equation, and we want to regress it against a short memory on the left side. And we see that in that context, regression or linear squares and that kind of thing is inconsistent on bias, and then we propose how to deal with that. For this presentation, I'm mainly going to talk about the first two chapters. Mainly, I would say focus more on the first one. And so, talking about the cross-sectional result. For mentioned, third chapter, co-authored with Daniel Asterrider. It was a postdoc here a few years ago, and Daniel Ventosa, who I mentioned at the beginning. And so yeah, that's that's the third chapter. So that's it. Let's move on to the first chapter, to this cross-section allocation result. So as I said, kind of one of the most common explanations why we have why the series may have long memory. One of the most cited, I would say, reasons to why we have long memory is this cross-section allocation result. So what Granger did is say we have a series that is actually an aggregated cross-section allocation of a bunch of AR1 processes with random coefficients of a particular way. Then that aggregated process is going to be a long memory process. And here look at the autocorrections. So what we're going to do, and what we did in the first chapter, so first we want to see which kind of long memory does this generate. It used to be the case that before we only focus on the spectrum or the autocorrelations. Now then we have more definitions of long memory, so people have used some other characteristics to say that we have long memory. So first we were interested in seeing if this process, this aggregated process, satisfies all the definitions that have been proposed. So that's kind of the first step. We want to see that it actually does. Then we know, and we want to see this, is an asymptotic result, so we need the cross-sectional dimension to go to infinity to start seeing this long memory result. And not forget, we want to see what happens if I just take a finite number of AR processes. If I just aggregate those, does that generate long memory? How many do I need to start seeing this long memory? So that's kind of the second result that we get in that chapter. And then we want to see is long memory, and we may be interested in seeing what happens if I try to take the memory out. Taking a memory out, taking a fractional difference. So we want to see what remains after I do this. Can I take the long memory out, and what remains if I do that? If I take the long memory, what remains? That's what the idea of the first chapter. With that said, as I mentioned, we have a bunch of definitions of long memory. Don't worry too much about all of those. The idea was just to show you that we have a bunch of definitions of long memory. Sadly, they are not equivalent in general. But yeah, we have a bunch of definitions. Kind of the first two was the typical that we used at the beginning. So kind of first, the covariance. That's related to the graph that I just showed you, that is going to zero kind of in a slowly manner, in an hyperbolic manner. What that means is that it goes to this, to k to the something, so that the autocorrelation function is a function of k, and it relates to k to the something. That would mean that it's hyperbolic. That was one way. The other would be the spectrum, as I told you, in this Granger paper. So if looking at the spectrum, it has a pole of the origin. That's how we model it. So when you go to zero, this goes to infinity. And then some other people have looked at how the variance of the sum, how that's the rate of that divergence. They have used this for breaks. So that mimics long memory behavior. So that was could be one way to look at long memory. It's a similar sense. So the idea here is kind of mimic what the fractional promotion motion does. So it should have the main characteristics of the series. No matter if I see it daily, or I see it weekly, or I see it yearly, it should have kind of the main characteristics. Here what we're doing is it should have roughly the same observation function if I observe it daily or yearly. That's kind of the main idea of that. And then, for the final, we say it's the distribution sense. If actually this process, when we go to in a continuous manner, it goes to a fractional Brownian motion, kind of the typical way to model long memory in continuous, for continuous functions. So yeah, bunch of definitions for long memory. With that said, let's focus a little bit. Let's focus on what we mean by this cross-section aggregation result. So say this. Let's start first with a simple example. So let's just consider one random AR process. So what we're going to do is, so typically we start with this AR1 process when we study, let's say 10 series. So this is an AR1. What we do then is we say this alpha is a constant. Given that it's a constant, we can estimate what we can calculate the moments, so the expected value, the covariance, and the variance. So we can do that given that it's a constant. What we're doing now, and what Robinson did, is what happens if this alpha is actually a random process. And it's modeled by this particular distribution, this beta distribution. So what we're doing now is not saying that it's fixed, it's some particular random coefficient. So in a sense, what we're doing is getting a family of AR1 processes. So what we're going to see is what kind of behavior does this family of AR1 processes have. This random coefficient AR1 model. And that's what Robinson did, 1978. And he calculated the moments. So see, it is actually, you can calculate the moments, but kind of behavior we should expect. And how to see it, kind of in a simple manner. So we have a random AR1 process. So an AR1 process. So we want to calculate the covariances. We know this. So that's gamma here is going to be covariance for the decay covariance. We know that is the expected value of the product of these things, given that it has expected value of 0. That can be expressed as the expected value of this kind of the thing on inside, conditional on the value of alpha. So we know alpha is a random variable, but we can still make this kind of use this. This is composition. So condition on alpha and then taking the expected value given alpha. And so just condition on alpha, we obtain the typical the typical autocorrelation function that we expect for an AR1 process. That would be kind of, if it were a constant, we would end up there, and that's the correlation function for an AR1 process. So what we do it now, then, now this is a random process, we should calculate the expected value of that, and that's just replacing the beta distribution, and we obtain this function. There, as you can see here, at the beginning, it doesn't depend on k, so that's a constant that I'm showing you here. So it's just a constant in terms of k, and then we have a ratio of gammas. These ratio of gammas we can show using student approximation. That actually this looks like, when k goes to infinity, it looks like k to the something. So we obtain this hyperpolitic k, this k to the something that we wanted to get from the beginning. Still, the problem with this random AR coefficient is that it's not ergodic. What I mean with that, let me show you kind of a graph to, I hope it helps to tell you why is that the case. So what I do here, I have the beta distribution on top, so I'm going to sample this this coefficient from the AR1 process, and below I'm going to show you the autocorrelation function that it relates to that particular coefficient that I sampled. So let's start with the first one. Let's say I just sample, I take 1 out of there, and it turns out that it's 0.2. So given that it's 0.2, then my autoregressive process, it just gets this autocorrelation function that we know of. So it's a short memory, it's one of the short memory. You can see it goes to 0 to the 5 picoseconds is already 0. So it doesn't seem to be showing this hyperpolitic that we want. And that's just sampling for one of this. Let's sample another. So now it's 0.8. So it's a little more persistent. That's when I showed you at the beginning. So it's a little more persistent. Still, it goes to 0 after 20 lags. So still, it's not the hyperpolitic case that we wanted. And on top of that, it's not the same correlation function that we had before. So if from the first sample, we had the blue one. Second sample, now we have the red one. So that would mean that it's not ergodic. If I do this and I sample 2 times, I don't get the same autocorrelation function. So that is not an ergodic process. We can, of course, do this again. So now we have this yellow dot, and then we have something in the middle, not the same autocorrelation function, and conditional on this value of alpha, we are getting short memory. We are not getting the long memory that we can expect. Well, the expected value of alpha. Yet, you can see from the beta distribution, we have a bigger mass kind of away from 1, so we have all of these regions where we know, from donate from there, we know that this is short memory processes, so they behave, let's say, in a nice manner. We know also that when we go in a pure AR1 process, when we go near 1, so almost a uniroot process, it starts to behave in a certain manner. It gives us some particular problems, and we can still sample from that side. If we do that, we can sample, for instance, 0.98. It could be randomly, we get 0.98 from there. If that's the case, then we get this autocorrelation function. So this is still short memory, but it's almost a uniroot process. So that's why we see this decay that seems slower, but it's just a matter that it's almost a uniroot process. So what Robinson, and I can do this and just sample over and over and again. So what Robinson is telling us is that we have a bunch of distribution, kind of a mass on this side, that we obtain these autocorrelation functions kind of near 0, and then we have some mass, little mass, near unit root, when we obtain autocorrelation functions that kind of goes on top. So when we take the average of this, if I were to do this all over and over again, I would expect to get something in the middle of those. So in the middle between the short memories, these ones here, and the almost unit roots here. So we obtain something in the middle. That's the average, that's the expected value that we wanted, and that's what Robinson proved that you can do it. Nonetheless, no matter how many times do I sample from this beta distribution, I'm going to obtain an AR1 process. So conditional on this alpha is going to be either this or this. I don't get the long memory that I wanted, so I get one of the two. So that's what we mean also that it's not a ergodic process. We don't get the autocorrelation function of the main process, let's call it. So that's what then Granger says, well, let's then consider, instead of just sampling 1 by 1 and see how it looks, let's just sample n of those, bunch of those, and take the average. So that's what we're doing here. Well, kind of weighted average. And so that's the main idea. Now what we're doing is just, instead of doing 1 by 1, just sample n of those. Let's take a cross-section again of those. And You can show also that this also behaves, it also gives you the same autocorrection function as the random AR process. The idea is pretty much, and that, yeah, that's definition 1. And it's pretty much the same process that we did before. So the autocorrection function depends on k, it's expected value of the product. Then we can take the 1 over square root of n, so it goes out. They're independent, already mentioned it, but the alphas are dependent, so we can use the sum of these expected values. This is that as we had before. So we get to this same expression. So unconditionally, if I were to say, well, I'm just sampling it, and they are random, and then the expected value of this is the same that I had before. So it's the same one, n times it's the same, and divided by n. So I get the same thing. The nice thing of the result of Granger is that it's even conditional on those values. If I take this so I take n, a really big sample, what saying is even conditional on those values, so not even taking the expected value, just sampling a bunch of those. What we did is getting kind of an average of this, so we know this goes to the expected value. So again, even conditionally, we get to the expected value. So this function that I showed you a few slides ago. So we get in this hyperbolic decay that we want. On top of that, turns out that this process now is a god. When we consider a big sample, in the n of those, it turns out now we achieve ergodicity. What I mean by that, so it's the same graph as before, just one line more. So we have our 4 that we sampled before. What we consider now, that's what Granger proposed. Say instead of going 1 by 1, let's just take the 4 and take the average. The average and the combines. So that's what the light blue line we have here. So you can see here, we're doing right away. We are constructing the expected value of those. So just by construction, we are getting to the expected value. And this process now, the sum of these 4, now we get the duration function, the long memory that we want. And you can think about if you take big n of those, so we get a particular mix of alphas coming from this distribution. So if it's a big enough, and I take another big enough, we will get, the intuition is we will get probably the same proportion of alphas in one back on the other. So we will obtain approximately the same autocorrection function. So that's what makes it ergodic. Just considering a bunch of those on one side, a bunch of those on the other, coming from the same distribution, we expect them to have the same autocorrection function. So that's what makes it ergodic. And so the first contribution I interpret, all this to explain what the coefficient against result is. So the first, and how we obtain the autocorrelation. So the first all of the papers we say, well, we know the covariances decay hyperbolically. That's something that we know from Granger. But does it satisfy the other definitions of long memory? Is a long memory in the other senses? And yeah, we do, and we prove in the dissertation. So once we have, for the first 4 definitions, we don't need nothing else. So just, given that we have that autocorrelation function, it's just a matter of just doing the calculations on algebra there, and we get that they satisfy these other definitions. I want to go to the algebra, it's of course in the dissertation. And then for the last one, probably the more resistant one, if we allow this, before this epsilon were just white noise, if we allow them to be an ID process, so what's going to happen is then what we can do is take the central limit term. So recall we have these n AR1 processes. So what we can do is just kind of taking the first element of the MA infinite representation of these AR1 processes, take the central limit term in that particular, the first element, that's going to be a normal. The same for the second element, it's going to be another normal. So we ended up with a sum of our normals. That's a general fractional process. And with that, we can show that then this converges to a fractional ground image. That's kind of the main idea, the first result of the paper. So it does satisfy the 5 definitions of the memory that we said. Still, it's an asymptotic result. We saw we needed this n being big enough so that we can get this autocorrelation function approximating the expected value. Or we need n big enough so that the central limit term starts to kick in. So it's an asymptotic result. We need a bunch of those. N goes to infinity. Still, we can ask ourselves, what if I just take a finite number of those? Do I get one when a finite random bunch of AR processes? So what we're going to do is we're going to do a Monte Carlo simulation, seeing if that's the case, how many do I need, in what do depend. So that's what we're doing, second result. So we want to do a Monte Carlo simulation. We want to see 3 dimensions. So we want to see how this depends on the long memory. So if I want to generate a larger degree of memory, a smaller degree of memory, is the same correlational dimension, do I need more, do I need less, depending on the memory. Then how many do I actually need? So how many AR1 processes do I need to start aggregating to start seeing the long memory? We want to see if it depends on the sample size. So it's another dimension we want to see in the Monte Carlo. And then we want to see, just for comparison, so we know with this we can generate long memory. We want to see how this compares to just taking a fractional difference or white noise process. How do they compare? So that's kind of these tables is trying to show you. So how they look. If I try to generate memory of 0.45, that's the theoretical value. If I want to do this with the cross-section I get it, the process that I will show you, this is the memory that I get it. If I want to just do a fractional difference or white noise process, this is the memory that I get. As you can see here, I wanted to do 0.45. With the cross-section aggregation process, we have the KPH, the local whittle estimator, and the maximum likelihood estimator. In the dissertation, we have another two, the Andrews Kuchenberger, also semi-parametric. One of the paper, this chapter is already in review. And one of the things that Paris asked us was to see what happens in the maximum likelihood estimator. So that's what we're showing here, kind of just to, for completeness. So even considering the maximum likelihood estimator, still we are not getting, we are getting more memory than we wanted to generate. And this just gets worse as we start to trying to generate even less memory. So you see 0.25, I'm over 0.3, no cases. And not the same with the fractional difference. The fractional difference is pretty much spot on, and even worse if I go with that. So what seems to, and even the days is robots, so they are getting more memory, the tree estimators. One of the things that I'm thinking is, so it doesn't seem to, we are not capable of generating exactly the memory that we wanted. And this is a big sample, 10,000, and 10,000 AR1 processes. So we are generating more memory than we wanted. So it doesn't seem to be as precise as just saying, well, let's take 10,000, why noise 10,000, just take the fractional difference. So it seems to be a little more imprecise than the fractional difference. Still, we get long memory, just a little more than we wanted theoretically to be. You can see this how this depends on the cross-sectional dimension. So you can see for a sample size of 10,000. So just starting with 50 AR1 processes. So what kind of, and this is showing us in a sense the distribution in a compact way. So for 50 AR1 processes, we get memory almost 0 to almost 0.7. So it's kind of, it's really uncertain the memory that we are generating. On the median is 0.35 when we wanted to generate 0.45. So this is theoretical that we wanted to generate. So 50 is not enough, it's really imprecise, and we are getting something, kind of all over the place. This, of course, an asymptotic result. We expect this to get better when we increase the cross-sectional dimension, and that's what we see. So here was a wide distribution, and then we see that it starts to converge as we increase the cross-sectional dimension. Yet, as we saw on the table, when we get to 10,000, we are generating a little more memory on the median that we wanted. Still, the distribution is kind of around that particular theoretical value. We are just, on average, getting more memory than we expected to. Yet, we are seeing that it actually converges to, starts to kind of converge to around the theoretical value, a little more slower and a little imprecise, but it seems to converge to the theoretical value that we want. Then, just to see how this relates to the sample size, so I'll show you here is the mean of the values that we generated by cross-sectional aggregation. We take the theoretical values. So in a sense, we wanted to see this is the bias, let me call it, of the estimator. So the red one on below, on the bottom, it's telling us that we are generating more memory than we wanted, so way above 0.45, that was we expected. And we can see that if that happens with a sample size, with a small sample size, to all cross-sectional dimensions, we are getting more memory. Maybe the case that the estimator is, we don't have enough data to start actually seeing the right value. Yet, if I get just fixed 50 AR1 processes and I start increasing the sample size, we are getting to the green area. That's the area that we want. That's the theoretical value that we want to generate. And as we go over there, we start to see less memory. So we kind of going back to the short memory. So as we increase the sample size, the test is able to say, well, this is actually not a long memory. Maybe it's just a bunch of AR1 processes. Yeah, it's a little above. It doesn't get us to 0, so it just reduces the limit that we want. So in a sense, we want to be in this greenish area. So we want to, if we want to get a big sample size, we should as well increase the cross-sectional dimension. So we have to do this. At the same time, increase forward. So I'm just going to sum it up. So small cross-sectional dimension. We saw that the values are below the mean for all cases. If the cross-sectional dimension is smaller sample size, the memory appears to be exaggerated, so we are generating more memory than we wanted. Maybe the case that the estimator doesn't have enough information. for the reason. Yet, what they both suggest that if we want to get a big sample size, we should also increase the cross-sectional dimensions. So we want to do 10,000 observations, we probably need a bunch of layer 1 processes to get there. And so in summary, you want to generate long memory by this procedure. It's not as precise fractional differences as we saw in the table, so we are generating more memory than we wanted, not as precise as just fractional differences. And it's more computational dependent. So fractional differences now using the fast Fourier algorithm that we have now is really, really fast. And here generating 10,000 layer 1 processes takes time and just for one series in particular. So it's computational dependent, it's not as precise. So yeah, not that for simulation purposes. Yeah, so come back. So we know it's a long memory. We want to see how this relates to the typical memory, the typical process that we use to simulate long memory, so the fractional difference in operator. So we want to see the relation between the division and the affirmation process. And the next step. So as I said, you're interested in seeing what happens if I take the fractional difference of this particular process. Can I take the memory out? And that's what this Y process is doing. So we have our cross-section aggregated process from before. Now we're going to take a fractional difference of that. And we know the theoretical value, we know the right D. So we're going to try to take the right memory out of there and see what we left out with. Just for the demonstration purposes. So this is just replacing XT. We know it's the average of this. And then the fractional filter is the linear process, so you just can go there. So what we're doing at the end, what it's trying to show, is that YT is a cross-sectional aggregation of Arfima 1 minus T. We call XIT as an AR1, and we are fractional difference in that, so it's an Arfima 1 minus T. So what we do in the next turn is getting the integration function, so seeing what kind of process we let up if I do this, if I try to take it to memory. We obtain this expression. It looks a little nicer here than it should be, because I'm just adding up a bunch of things in this F1, F2, this complicated expression. Nonetheless, it has two main components. So yeah, this is the correction function for Y, so the fractional difference. It has this gamma star. This comes from a fractional difference. So from this is the correction function of an I minus D process. So on an over difference process, so one that we take more memory, so we go to the negative side of the long memory. These anti-persistent processes. So just by doing that, we are introducing some component of the autocorrection function into the aggregated process, and then the rest it just comes from the aggregation process. So just by aggregating, we get this other function, and then this from the anti-persistent process that we introduced in a sense. Another thing to how we show this, the same idea. So it's the correction function is the expected value of the product. Kind of the same idea before. Now we have this product of Arfima 1 minus D. We know from Sol, 1992, just put it there. This is the correction function of an Arfima 1 minus D, and then as before, it's gonna be a function of alpha I, and then we just can get the expected value of the alpha I. And of that function alpha I, and that's gonna be our autocorrection function. Another thing that I forgot to mention, this autocorrection function, it is not the same as the one. It doesn't come for a normal process. So what we did, we tried to take the memory. Still, what remains is not a normal process. Something that I'm going to go back and because I just noticed that it's not a normal process. Yet we can see and we also see this in the corollary. So we are interested in what happens if the autocorrection function goes to infinity, so k goes to infinity, how this looks. And you see here it shows this hyperbolic decay. This, I would say, is inherited just by doing this fractional differencing. So we introduce this gamma star, and that's what I say is governing this behavior as we go to infinity. So it seems to show hyperbolic decay, but nonetheless, we can also show that the autocorrelation are solvable. And that's one of the characteristics that Davidson used to say that a process is an I0 process. So they seem to go slower, let's say, but they are summable. So they still go fast enough that they are summable. So they still are an I0 process. So yeah, yet they are not a normal process. So it's a different process that we're dealing with. So just to give us an idea, so what we're doing here is the yellow line is the fractional difference of this cross-sectional aggregate process. So if this were an ARFIMA process, this should look like an ARMA process, which show it's not, just for the graph, the plot, so you can see it. So even to 50 periods, it's still not quite in zero, so it's showing this is the probability thing that we show. Still, we know it's an I0 process. It has population functions, the operations that are summable. So we may be able to approximate it with an AR or an ARMA process. That's what we're trying to do in this graph. So here we feed an AR process. So using the lags, using the basic information criteria. So just a pure AR process, we are able to capture, I would say, even to the 5th lag. It's almost close there. It's close enough to the theoretical one. Yet, in the case fast, it's a short memory process. So after 20, it's just 0 from there on. So it ranges after that. The ARMA works a little better. So I would say you approximate this even to the 10th period. But after that, it just becomes fast. So again, just showing this is not a process where we let off with. Still, we may be able to approximate it to some periods. That's just by the sense that we are using some flexible AR process, so maybe we can approximate it. But still, it's a short memory process, so we are not able to capture the whole decay of this hyperbolic sense. So yeah. So just to sum up. So taking the fractional difference, we get a short memory process, so it satisfies the Davidson definition of short memory process. It has autocorrections that are summable, absolutely summable. And yet, the process that we remain with is not an ARMA process. We may be able to approximate some periods ahead, but it's not an ARMA process. We cannot totally approximate it. And yeah, that's kind of the third result from the first chapter. So we know it's an ARMA process, yet the typical process that we use to simulate or to forecast long memory is the ARFIMA process. So what I did in the second chapter, yeah, just going back, so we know that it doesn't come from fractional differencing, it's long memory, doesn't come from fractional differencing. Still we say, well, the ARFIMA process is one that we know well, we know how to simulate, we know how to forecast it, yet what I'm trying to do is, well, let's try to evaluate what happens if at this particular process I try to feed an ARFIMA. Can an ARFIMA make good forecast on that? And that's what the chapter 2 is about. So we're doing this, so evaluating. So I'm going to generate some long memory processes that doesn't come from an ARFIMA, yet I'm going to feed an ARFIMA and forecast it and see how well does it forecast. In the chapter, I consider the cross-section aggregation process that I showed you, we are more familiar with, and also the duration model that is also an ARFIMA. Here, for presentation purposes, we are familiar with the cross-section aggregation, so I'm going to keep up the cross-section aggregation, but in the chapter we also have another process. How to evaluate, we compute the root mean square error, so how much they differ from the real value, and then the model confidence set. What the model confidence set is, so what is a process that we can, from a starting set, we say we are going to select these, let's say, 10 models. You want to see from those 10, which are the models that forecast the best, which are the best performing models of that. It's a process that is developed here, well, here, I guess. Here, I guess. So yeah, and the idea is just to take this, the best performing models of that set. So we're going to use those measures to see if the ARFIMA is a good forecaster for this particular process. We are going to consider 6 different horizons, so kind of just trying to forecast the next five values we saw from the graph before. 5 values, we may be able to do it with a high order AR process, but then we want to see what happens if I go higher horizons, even 300, probably too much, but yet if you want to do some big long horizon forecast, like trying to forecast the climate at the end of the century, that sort of thing, maybe 300 periods ahead is sensible in that context. So we may be interested in seeing what happens 300 periods. So for presentation purposes, also I'm going to just focus on these 6 models. In this chapter there are 15 in total, so just here just to make a little simple, let's focus on these 6. So first we're going to consider this high order AR process following Ray, and also kind of an idea of the graph that I just showed you. So we have maybe a high order AR process can approximate this function well enough. And then we also consider the heterogeneous autoregressive model of Corsi. So it's a constraint AR22, and the idea of this And this is just mainly in a finance context, I would say. So it's an AR22 in a particular manner. So what Corsi said is we have some particular value. We have agents that respond to changes daily, so they want to update the positions on a daily basis. So they are, I would say, the fast in F of those processes. So they want to update daily. Nonetheless, we have some other agents that don't want to update daily. That maybe they want to wait until the end of the week. So that would be the second component, the weekly components. So they may only want to update after the end of the week. And then probably some agents that don't want to update that frequently, maybe they can wait till the end of the month. So in a sense, pension funds, that kind of thing, they don't want to update frequently, they can wait till the end of the month. And what we end up with is this model that actually reacts to the three agents, the daily, the weekly, and the monthly. So it's, again, you see this is an AR22, just replacing. Nonetheless, we are restricting the coefficients, so all of them have to be the same as A3 from the sixth line and so on, and then also just one coefficient for the weekly and one for the daily. So we are estimating just 3 coefficients instead of the 22, and that we see may help for forecasting. Just another, so that relates to the hard 3 is related to the R22, just also for completeness, I would say. We consider the AR50, and we want to see how it compares against a similar hard. So what I'm doing here is I'm defining this hard 4. So to include a fourth element that is actually the 50 periods. So in a sense, it will be an agent that responds until 50 flags. What it does is it's allowing us to just estimate. It's an AR50 just with 4 coefficients to estimate instead of 50. There 9. Let's see how this behaves. Here I'm just going to show you the model confidence set results. For these 6 models, the dissertation we have way more graphs. So here we have, so in blue we have the fractional differencing. We have the hard 3 in green, light blue, they are 22, so I would say they are related. The same with the yellow and the red, and then the I1 process. So, and we have here how the percentage of times that each model falls into the model confidence set, so how many times in average they are selected, they are the preferred model for different for different horizons of 5 periods ahead, 10, 30, 50, and so on. So we can notice kind of right away the fractional differencing right away is the second preferred. Turns out that just the I1 process, so just leaving the last value as a forecast well enough for 5 periods, even 10 periods. So it's a good forecast. Sadly, something happens, we want to do a big model, bunch of dynamics to try to forecast best. And turns out that just given the last value, sometimes it's the best forecast, and that's the case here for 5 periods, even 10. But as we increase the forecast horizon, that's when the long memory, I would say, the fractional differences start to give the gains of using fractional differencing. And we see for 30, we already, fractional difference still is gaining ground to the I1, and it's actually on top of that. For all degrees of memory, so as I mentioned, so we have the memory of 0.1, 0.2, 0.3, 0.4. This is the degree of memory that we generated, and how well do we deny forecast using the fractional difference model. So that's one thing that we can see. As we increase the forecast horizon, the fractional difference seems to behave the best. So we can use this model to forecast cross-sectionality process. They are not enough maps, the fractional difference seems to behave well for long horizons. Another thing is in here to notice is to compare between the AR50 and the hard, for instance, so between the red and the yellow, or the light blue and the green. So the red here, and then the yellow, this is the most flexible, so we are allowing the 50, estimating them at once, so 50 things to estimate. It seems to give us good forecast at the beginning, so 5 periods ahead, it gives us the best performance, well, comparing against the hard 4. So this restriction doesn't seem to begin giving us any gains at some periods ahead, just some small periods ahead. But as we increase the horizon, I would say it goes into this variance trade-off. So we have more things to estimate, that increases the variance. May reduce the bias, but it may not be so much that we are starting to see that it starts to losing ground against the constraint AR22, the hard 4. For 3, they are pretty much tired, and then you start seeing they start to gain ground. So in a sense, what it's telling us that just imposing this constraint, instead of estimating all of them, we can reduce the variance, and that seems to give us better forecast performance against the unconstrained when the horizon is big enough. For smaller horizons, a flexible AR process seems to give us the best performance. And the same story holds with the R3 and the R22. And the same idea. The constraints doesn't help at the beginning, but as we increase the horizon, seems to give us a little advantage of using these constraints. So, that's kind of just summing up. So the figure shows that this fractional difference in model seems to give us good forecast, especially if the horizon is large enough. So we're going to do some long horizon forecast for this process that is not ARFIMA, yet using a fractional difference seems to give us good performance. And comparing between the HAR and the AR and the high order 22 seems to, as I told about, seems to point out to a bias variance trade-off. So these flexible AR processes, it may reduce the bias. We are allowing the model to approximate it better, but we estimate more parameters. That, of course, augments the variance. So we are kind of going to this bias variance trade-off. So what it's telling you, what the figure is telling us, suggesting us, is that these constraints seems to help us when we go to the bigger horizon. So just reducing the variance seems to give us a little better advantage than using a flexible AI process. And that's what it's here. So just, if the horizon is good and is long enough, just allowing some constraints help us to do some data forecasting. And you can see that's what happens with the fractional differencing. So it's the more constrained, we are just estimating one parameter, and it seems to be reduce the bias so much that we are getting the best forecast performance out of those, considering this graph, this figure. So, just to conclude, kind of what I'm going to. So, in the first chapter, we showed that this cross-sectional regression result is satisfied broad definitions of long memory. So it is long memory, many more definitions, but yeah, difficult to use. It's an asymptotic result. We saw that in final samples, we do generate long memory, but it's not as precise as just fractional differencing, and it's more computational than memory. So for simulation purposes, we can generate long memory, but it's not as precise. Not even more time consuming. We saw the behavioral limiting properties of the fractional differencing. So we saw we can take the memory out, we are let out with a nice zero process, but it's not an ARMA process. So we have to be careful if we want to feed an ARFIMA process to this. It's generally not going to be correctly specified to estimate an ARFIMA. So that, nonetheless, for forecast purposes, it's good enough when the horizon is large enough. So it's not an ARFIMA, but yet if I use an ARFIMA to forecast it, seems to do well enough when the horizon is large. And